the speed that sound waves travel through air is incredibly fast, faster than most humans ever go. How can we measure something that travels so quickly? This is measuring the speed of sound using an echo. Using sound waves to locate an object is called echolocation. Knowing the speed of sound through air or water is crucial for echolocation to work. Bats use echolocation instinctively to navigate in darkness. Echolocation is the primary objective of sonar. It was developed after the Titanic famously failed to detect an iceberg in the dark. In this lab, we'll use a sound sensor to measure the time it takes an echo to return to its source. Using the travel distance, we can estimate the speed of sound. To help detect the echo, we have a long tube that will constrain the sound waves and screen out background noise. Anything can be used for this purpose, even rolled up paper. It helps to have a long tube so there's more time between the signal and the returning echo. This tube is 1.2 meters long. I've closed off one end with a piece of cardstock and placed the wireless sound sensor at the open end. I'll produce a sound by hitting these two markers together. Almost anything can work for this purpose, but it helps to have a sound of very short duration. It can be difficult to measure the return time if the sound is still being produced when the echo returns. The sound sensor is connected to an oscilloscope display in SparkView. The x-axis has been adjusted so that it will show at least one echo. It helps to know what time to expect because background noises cause erroneous measurements. In this case, it should take more than 0.007 seconds or around that. The trigger level is adjusted so that it will collect data only when a minimum signal is detected. So there's the trigger right here. So I have it activated. Otherwise, background noise could swamp your signal, or if your signal isn't even setting off the trigger, you could adjust it lower. Once adjusted, we're ready to collect data. To collect data, I click on Start and tap the markers next to the open end of the tube. If it's loud enough to cause a trigger, the sound sensor measures the sound starting at time 0 and then the time of the returning echo. Once this happens, we'll click Stop to save the run. Otherwise, some other noise might erase our data. We'll repeat this 4 more times for a total of 5 trials. So you can see the first sound hit here at 0, and it oscillates for a little bit. You're getting reflections off the side of the tube, but then it should die down, and then boom, here's the returning echo. So the time from 0 to here is the time it took the sound signal to travel. And that is now run 1. So I can hit Start, and I'll look for a similar pattern. That was a little noisy. So it's not dying down as much here. And so this one, that's where the echo is returning there for run 2. A little harder to see. Again, it dies down, not much signal here, and then boom, there's the echo. That's run 3. So once you see the pattern, these ones with more noise, you can pull the signal out. But let's see if we can do a little better. So again, it dies down, And there's where the echo hits. So let's run 4, one more here. So we've got our data. Your job now is to do the analysis and finish the lab. The time it took to return can be measured using the coordinates tool. First, let's move back to our first run. Notice how I can unclick these runs and they appear. You can do more than one, but let's just do run 1. So time 0, that's when the sound started. I click on the coordinates tool, and wherever I move that, it tells me what the points are, the time and the loudness. So here's the sound has died down. I want to select the point close to right when the sound, let's get that out of the way, when it started to go back up again. So right there, I can read that time off. And so now we know the time that it took the sound to return to the sensor. So knowing the time and the distance, the speed of sound can be calculated. Be careful though, the distance the sound traveled in this time is not the 1.2 meter length of the tube. Would an echo be produced if the end of the tube were open? Let's remove the cardstock and find out. Let's start. So are we going to get an echo now? Turns out it does. Now it's easier to imagine the sound wave bouncing off that solid barrier of the cardstock. How does it bounce off an open end? When the tube is open, sound wave is a series of compression and expansion zones. When the compression wave exits the end, it leaves an area of low pressure behind, and the atmospheric air rushes into the tube, creating a sound wave coming back. So when the outside air rushes in, we create the sound, the echo. Something similar happens in many musical instruments like horns and organs. It turns out that music appreciation also means the appreciation of physics.